Okay, so as we look at section 5.4, logarithmic functions and models, first off, we have the graph of a logarithmic function, and mainly the graph of log x up here on the screen. Just to show you that it does not take up the whole entire coordinate plane. It is mainly graphed when x is a positive number is what it has to be graphed, and that's because we're not allowed to take the log of a negative number. We can't even take the log of 0. So with that in mind, our domain for a logarithmic graph is typically from 0 to infinity. The range goes from negative infinity to positive infinity, because even though it doesn't show here, as x becomes a really, really small decimal, the y answer is something really big in the negative direction there. So, as x approaches 0, like 0.00001, as we do that, the y value is going to approach basically negative infinity. It's going to be really big negative number is what ends up happening. We get to do some evaluating of two main types of logs that we do here. Evaluating logarithmic expressions, we have log and then ln. Log, basically, when we see it written in that standpoint, is assumed that we are doing log base 10 mathematics, and that's what our calculator has built in. We can do logs with different bases, and we'll experiment that throughout the course of this chapter. But our calculator button is figured out, is primed and set up to be to evaluate just normal base 10 mathematics, because that's what our place values are. We go powers of 10. We go 10, 100, 1,000, and so forth. Now, ln is technically log base e, is what ln stands for. That's the natural log. And so that's using a specific base. E is roughly 2.718, blah, 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 as a decimal. So that's calculating things based on that base instead of doing base 10 mathematics. But at times answers can be done either way. It just depends on what type of problem or situation is arising in your science field and so forth. You probably find using ln more often is what's being used, the natural log, to be able to compute things, as opposed to just in a normal mathematical classroom. We would just use log base 10 is what we'd end up doing. So with in mind here, they asked us to go through to simplify the logarithms by hand, which means don't use a calculator. So what they want us to try to go through to do is for example, for A, is they want us to rewrite this. They want us to rewrite, and there's a reason. They want us to rewrite it so that the number after the word log, so in this case the 100,000, we want to rewrite it as though it's 10 to some power, because we know when there's no little number down by the subscript about where the G is, the tail of the G, we know it's base 10. So our goal here is to say, well, 100,000 is the same thing as 10 to the 5th power. So I can rewrite this as 10 to the 5th. And then what I'm able to do here is I'm able to cancel those out, and then I'm able to say my answer is 5. And then on part B, if I have log of 1, so what we have to think about, I can rewrite this as log base 10 of 1. Well, how can I rewrite 10 to a power to get 1? Well, that means I can rewrite this as log base 10 of 10 to the 0 power. And then I can apply this property where those things, when it's when the base is matched, the base on the logarithm and the base of the number being raised to power, we can go through, and then that's what the calculator does. The next one gets a little bit more challenging rewriting. Again, it's a lot easier to just plug them into the calculator. So if I'm doing the log of 1 over 1,000, I'm going to rewrite this as log base 10 of, technically 1,000 is 10 to the 3rd power, so this would be 10 to the negative 3 power because it's a fraction. And then I can cancel these, and that equals negative 3. Then on D, I can rewrite log square root of 10 as log base 10 of 10 to the 1/2 power. Now those cancel. I get 1/2. And then we finally get to the last one, e, and they asked me to do the log of -2. And this goes back from the standpoint of what I mentioned earlier on. Cannot take the log of a negative number. Cannot take log of negative number. So this one, we would say that it does not exist. That answer does not exist because there's no way to raise 10 to a power to get a negative answer. Because again, if we go back to look at the graph here, there's no time for me to get a negative y answer on this side of the picture. So that's why we get to say it does not exist, because there's no way to get 10 raised to some power to equal a negative number. It just doesn't happen because there's nothing graphed on that portion of the graph. All right, so with this in mind, we get to use some properties, and I've already started using one of those to do some of that simplifying. One thing we do know that is if I have log of 10, or basically log base 10 of x, to the x, those cancel, and that's what that property I was using. The other thing we can do is if I have 10 raised to the log of x, then the 10 and the log cancel, and I'm left with just the x is what I'm left with. And then these next cases are just in case we are doing other base mathematics, like if they ask us for what is the log base 2 of 2 to the 5th power? Well, the answer here technically is 5, because whenever the base and the base on the logarithm and the base of the number being raised to a power, whenever they are the same, then we can say that these two things just cancel each other out, and I'm left with whatever the exponent is. Then vice versa. If I have 7 raised to the log base 7 of x, then what this says is I can cancel those two things, and I'm left with the answer as x. Again, usually they don't give us a lot of those problems in the easier formats. Usually we have to do some simplifying. So an example of where we got to simplify is if they say, hey, without a calculator, log base 4 base 4 of 64. Well, we can rewrite this as log base 4 of 4 to the 3rd power. And then now, based on the property, the log base 4 of 4 cancels, and I'm left with the exponent of 3 as my answer. And so same thing would apply if I had like 32, do I want to say that? No, I'm going to hold off on that one. Because the number I was going to give here, an example, was going to have to do a lot of extra steps, but we could do it. Well, why not? We're a college class, we can do it. If I have 32 raised to the log base 2 of x, let's say, I can rewrite this as 2 to the 5th raised to the log base 2 of x. I can use an exponent property, power to a power, and I get to rewrite this as 2 to the 5 times log base 2 of x. Then we can use a logarithm property that I'm going to teach you in one of these sections here, and we learned in Algebra 2, the 5 gets to come up to be a power, and this becomes 2 to the log base 2 of x to the 5th. Now I can go ahead and cancel the 2 in the log base 2, and my answer is x to the 5th. Again, a little bit complicated, more advanced one for right now, but that we will get there as we look at the course of this section and the next section that we get to tackle with this chapter. So they asked us to use inverse properties to evaluate each of the following. And so with that in mind, they want us to use these properties up here, the inverse properties. So with that in mind, for A, they say we have log base 6 of 6 raised to the negative 1.3 power. Again, since I have my base of my logarithm matches the base of what my power is, those things cancel, and my answer is just negative 1.3. On part B, I have 5 raised to the log base 5 of x plus 8. Again, this is where we get to use the second property. The base and the log base match, those cancel, and I'm left with x plus 8. And then for C, again, even with fractions, my base matches the base here, so that means I'm just left with 45. And remember, that log is canceled out too. When you cross out the left stuff, it takes away the word log as well. Again, pause, replay if you need to. Converting between logarithmic and exponential form. And we do that in order to help us solve logarithmic equations when we're trying to find the value of an x somewhere in the problem. And so we use the process where no matter what my base is, if I have log base a, so base, it could be log base 2 of x equals k, then what I'm allowed to do is rewrite this as the base to the answer power equals the number or whatever's after the log, is what that's saying I'm allowed to go through and do. That's what it's indicating. Now, where a has to be a positive number, so I can't have negative bases for the logarithm. A cannot be equal to 0. And then also k is a real number, so it can't be like the square root of -2. The function given by f of x is equal to log base a of x is called a logarithmic function with base a. Whereas if I have f of x equal to log of x, then we say this is a logarithmic function with base 10. Because again, when there's not a number there, then I get to say that it's base 10. Again, we convert between the two formats so we can solve logarithmic equations. So we need to go backwards and forwards and forwards and backwards. Inverse operations of logarithms and exponential functions is our next focus. Is how do we solve for the letter x? So we're going to use our notations of rewriting so that we can go through and solve this. And we can do it with the calculator is what we're allowed to do. So here, since they're giving everything is in exponential form, it's in exponential form, we're going to convert to log form. So I'm going to write the word log in there. So again, we're basically coming back up here and starting with the right side and going back to the left is what we're going to do. We're starting with exponential, rewriting it to look like the stuff on the left side. So what we do is we know we want to bring the word log in. So log, and then I got to fill in 3 locations. The base, what's here, and then an answer. I got to fill in 3 places. So first off, wherever we see a number being raised to an x power, so in this case it happens to be the 10, that lets me know what my base is. So this is log base 10. The answer goes here. And then whatever was the exponent goes in the other spot. So, if you want to look at it, it's log, and then we look at our base, and then we have the answer equals the exponent. So when we're in exponent form, the exponent is the final answer in the logarithmic form. The answer from the exponential form is technically what's after the log, and then whatever is being raised to a power is technically the base. So we're going to do the same. So as we have that, now that we know we have log base 10 of 0.001. Again, if we want to use the calculator, we can use it. So where we can rewrite it like I did up above. We're going to speed it up and say, okay, what is the log of 0.001 in the calculator? So as I grab the calculator, I'm just going to press the log button, which is right there highlighted in the red box, and then type in 0.001 and then hit enter, and it tells me that x is equal to -3. And we're going to now do the same thing with part B. Part B, we start off with 10 to the x equal to 55. So now I can rewrite this as log, sorry, don't know why I did that. Log, my base is 10. The answer goes next, and then the exponent goes after the equal sign. And then now I can go to the calculator. Remember, we don't have to type in base 10. There is a way when it changes that we can do it, and that's in another lesson. So I'm going to go through and press log of 55. And I get x is approximately 1.7404. And again, we would round it accordingly. And let's see, the last one here, C, 10 to the x equals negative 1. Well, let's see, I would rewrite this as log base 10 of negative 1 is equal to x. And again, we go log of negative 1. And it says non-real answer is what it says here. So that tells me that x does not exist. Which means that there's no value for x that you could put in there to raise 10 to that power and get a negative 1 for an answer. That's what that means. There's not a number that occurs. All right, so now let's solve more complex versions with that. Eventually, we get to do the reverse process in the lesson, and then start solving some word problems. So, not a bad lesson. The next lesson, we get to actually do different bases and expand and condense. So this is not a bad first start. So I want to solve for x. So I need to do some inverse operations here. So first thing I'm going to do is I'm going to divide both sides by 4, because my goal is to rewrite it in logarithmic form, but I need to make sure I remove as much as I can until I get that base exposed. So I'm going to divide by 4, and we get 10 to the 3x equals to 61. Now we're going to rewrite it in our logarithmic form. So log base 10 of 61 equals 3x. And then now I'm going to go ahead and divide both sides by 3. And I get x is equal to the log of 61 over 3. So let's go to our calculator. And I'm going to do fractions. So alpha y equals, give me a fraction. On top, I'm going to do the log of 61. Now, anytime you're using a logarithmic button or a natural log button, the ln button, close the parenthesis when you're done with it. That way it lets the calculator know, hey, I'm done putting stuff on the inside there. And then I'm going to arrow down to the bottom, put in our 3, and then I'm going to hit enter. And x is approximately 0.5951. Again, round accordingly to what they tell you. I'm taking it out and round it to the 4th decimal. Example 9 has a couple different cases here, so we're going to go through and solve each one. Now here we're reversing the process. Here we're remembering that technically it's log base 10 of x equals k. So when I go to exponential form, then I get to say 10 to the k power equals x is what I'm able to rewrite it as. So that's the process we're going to do here. We're going to go through and say, all right, I know this is really written as this. Then I can say 10 raised to the 3rd power equals x. And then I can go ahead and say that x is equal to 1,000. On B, again, remember it's log base 10 of x equals negative 2. So 10 to the negative 2 equals x. X is equal to 1 over 100, or x equals 0.01. Again, the reason why I keep rewriting that 10 in there, because sometimes we forget that there's a 10 there. Sometimes we do a bunch of problems and there's another number there, so we see the number, raise it to like the 2.7, and then that's our answer. But now when there's not one really listed, we forget that there's technically a 10 there. So 10 to the 2.7 power is equal to x as I go to rewrite. Again, this is going to be a big answer. You think about it, 10 squared is 100. 2.7 is a little less than 3, so that'd be 10 cubed, which is 1,000. So this answer should be up in the hundreds, a good portion, probably above 700. So 10 raised to the 2.7 power. Oh, it's actually at 500. All right. I thought it was going to be bigger than that. There we go. All right. And a couple more. So we got one more easy one, it looks like. And then we have a word problem application. So, again, I still want to solve. The only difference is we got a multi-step problem here. It says 5 times the log of 2x equals 16. So 5 times the log of 2x equals 16. I cannot rewrite it as 10 to a power because of the 5. So what I'm gonna do is I'm gonna divide by 5, and I get log of 2x is equal to 16 fifths. I can turn that into a decimal because it is a terminating decimal. I wouldn't do it if it's a repeating decimal or some other type of decimal because it'll just take too. It may not be as accurate, so I'm going to leave it that way. And then now I'm going to rewrite it as 10 to the 16 fifths equals 2x. And then I'm going to divide both sides by 2. And I get x is equal to 10 raised to the 16 fifths power divided by 2. And that's what I'm going to type into the calculator. So alpha y equals, give me a fraction. Again, if you need to pause to catch up on the writing, pause the video. And then play it when you're ready to watch me walk through. Remember, alpha y equal gives me a fraction. I'm going to do 10 raised, and I'm going to do a fraction again. Alpha y equals, and it's 16 over 5. And then I'm going to arrow down to the denominator, and then I'm going to put my 2. And again, I would just get in the habit of typing the fraction in as the exponent, just to make it be as accurate as possible. And then I hit enter, and this tells me that it is 792.4466. We should say approximate. And the reason why we say approximate because we rounded. It didn't come out to an exact terminating or decimal there. It kept on going. All right, last one. The number of species of tropical birds on an island of different sizes, x near New Guinea, can be found by the following equation, where x is in square miles. If the number of square miles x of an island increases tenfold, how many additional species of birds are there? All right, so that's telling me tenfold. So I'm assuming that on A, they're telling me that x is equal to 10. So what is f of 10? So 39 plus 13 times log of 10. Now I can type that in the calculator. 39 plus 13 log 10, close the parentheses. So I can type that in. I will tell you it is 52 is what it's going to be. So I hit enter and I get 52. And the reason why I said that was because the log of 10 is technically 1 because it's log base 10 of 10. And so so I kind of had that little memorized. That way I can say, oh, that part's just 1. It's really 13 plus 39. Part B, determine both symbolically and graphically the size of an island that might have 50 different species of birds. Okay, so our answer up here on A is birds. So instead of us having miles, we got to figure out. We're not given the miles. We got to figure the amount of miles given the amount of birds. Now the nice thing is, we know our answer is going to have to be somewhere around the tenfold. because putting 10 in there gave us an answer of about 52. So I know it's going to be somewhere around that, probably a little bit less than it, or less than it, because we have 50 birds here as opposed to 52. So in this case, we're saying that f of x equals 50. So 50 is equal to 39 plus 13 log of x. So 39, we're going to subtract it. I get 11, equals 13 log x. Then I want to divide by the 13. I get log x equals 11/13. Now I'm going to rewrite it. 10 to the 11/13 power equals x. So 10 raised to the fraction power 11/13. And that tells me that x is approximately 7.0170. So less than 10. Okay, so again, that's how we work these basic logarithmic problems. We're going to expand on this in the next section, dealing with some natural logs and some other bases as we do things, and we'll get into expanding and condensing our logarithms in order to help us solve.